Extended conjugation lowers the energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, causing absorption to shift to longer wavelengths, so conjugated systems absorb light at lower energy. Think of molecules like a set of stepping stones for electrons. When double bonds or alternating single and double bonds join together, the stepping stones spread out and make it easier for electrons to jump from one level to the next, so they need less energy of light to make that jump. A simple isolated double bond might absorb in the ultraviolet, but if many double bonds are linked, the absorption moves into the visible region and the color changes. Conjugation increases the range over which electrons are delocalized, and more delocalization means a smaller gap between the electron's starting level and the level it can jump to when it absorbs a photon. Chemists use ultraviolet visible spectroscopy to measure the wavelength of light absorbed, and longer conjugation gives a bathochromic shift, which is just a fancy way to say the absorption moves to longer wavelengths. Students often think adding any group always shifts absorption the same way, but electron donating and withdrawing groups affect the shift differently, so the exact position depends on both conjugation length and substituents. Check the substituent effects rather than assuming length alone controls it. Another common mistake is confusing fluorescence with absorption. Absorption wavelength comes from the energy gap we just described, while fluorescence depends on what happens after absorption, so do not treat them as identical observables. A quick tip is to draw the conjugated pi system, count how many atoms participate, and consider whether attached groups push or pull electron density to predict the direction and size of the shift. For more videos and resources on conjugation and ultraviolet visible spectroscopy, visit www.gumballdegree.com.